Hey, hello there. So today's Leetcoding challenge question is called course schedule. We have a total of n courses we need to take, and they are labeled from 0 to n-1. Some courses may have some prerequisites, meaning that we have to first take certain course before we can take some other courses. So like, first I have to take calculus, then you can take a good probability course. So they are expressed as this pair of number kind of expression. So the course 0 require course 1 as a prerequisite. And the given the total number for courses as the list of and also a list of prerequisite pairs, we want to determine is it possible for us to finish all the courses. So the only case where we couldn't really finish the course is that there is a cycle. Let's say that if we need to finish course 1, we need to first finish course 2, and then we find out if we need to finish course 2, we have to first finish course 1. So that's the a simple cycle there. For that reason, we couldn't really never finish either course 1 or course 2 because they depend on each other. So yeah, so then this question is just we can realize that this question is a cycle detection question inside the graph. To be more specific, it's a directed graph, and the nodes inside this graph are the courses, and the edges are the prerequisite dependencies. So it's a directed graph. So let's look at some of examples. These two examples are too toy to be giving you any kind of insight. So let's just make a little bit bigger one. So course 1, it's a prerequisite to course 2, and course 2 is a prerequisite to course 3. 3 is a prerequisite to maybe a couple of things, 4 and 5. So, but before that, we find that course 2 is also a prerequisite to certain course, phonics course 5, maybe 6, and somehow that course 6 is also a prerequisite to a course 2. So there's definitely a cycle going on there. But before that, we find we'll go there eventually. But also that course 3 is also a prerequisite for course 5. So let's just imagine that we have to take all these courses. Maybe pad this 0. Now this worked too, right? Yeah, this worked too. So just looking like this. So just imagine that I'm a person actually taking courses. So obviously we have to have a little notebook to keep track of the number of course we have actually taken, and then it's the current passes that I'm taking inside this graph. So obviously we begin with 0, then we after taking course 0 or plan to take course 0 after we. Just imagine that we finished the 0, we can look at the course that we can then take after 0. We find we can take course 1, so we do that. After 1, we think we can either take 2 or 6. Just imagine it's a linear kind of sequence of the course taking, not parallel. Then we go to 2. We find that for 2 we can go to 5. After taking 5 is a terminal node. There is no course that depends on it. So at that time, we can safely say, yeah, we can definitely finish 5 if we can indeed finish, if the prior pass is no problem. But we're going to determine that later on. But for now, after we finish 5, we can say that, yeah, we can take 5. If everything that's happened before it can be okay. So then we backtrack to course 2. We see that there's another kind of a sequential of courses that we can go, 3 and 4. After we explore 4, we put 4 as taken. Then we keep backtracking and put course 3 as taken. After that, we find all the subsequent course after 2 has already been taken, so we put 2 onto the taken as well. Then we go back to 1. Then the funny things start to see. We see that after we finish 1, we can take 6. And then after we take 6, we find we can actually take 1 again. So then we find that the course is already on the path, meaning there is a cycle. So what we just illustrated here is that we can use a stack to keep track of the current path. Once one particular branch is taken off, we can mark all of those in the backtracking along the backtracking time to mark those as taken. So just gonna note down here. We're gonna do DFS search and mark course as taken. Doing backtracking. So this is a post order. And then the thing to detect cycle is that when we want to push a course on stack, and it's already there. That means there is a cycle. So that's 3 lines summarizes the whole approach. The reason that we mark this, we need to mark this taken doing the backtracking is that maybe once we finish 2, then go back to 1. If that 1 is totally okay, maybe there are some other branches like a 7 to 8, and 8 actually is a prerequisite to 2. So when we explore the path starting from 7, after 8 we would actually want to go to 2. If for that time, at that time, since we already mark everything that's after 2 and including 2 as taken, we would just avoid doing the duplicate work. So this taken here can functioning as the mechanism to avoid duplicated work. And the path is a stack to keep track of the current courses that we have taken to get to a certain course. Every course that either it's isolate or we have dealt with all the subsequent courses, then can be popped out of the stack and moved into the taken. So that's the explanation, sort of illustration about how to do DFS search to detect cycles here. So I'm just gonna code this thing up. Move myself up a little bit. So just lay out the attack plane, I guess. Do a little bit of graph processing. Since we got the edge list, we want to convert that into adjacency list. For each of the course, we're gonna have a list of the courses that's immediately subsequent. So for the item 2, the course 2, we're gonna use a vector or list to keep track. Have the course 3 and 5 in there. So when we're looking at course 2, we can look up at the subsequent course much faster compared to an edge list. After that, we're gonna do the DFS function. It's gonna return whether there is a cycle or not. And we're gonna try to do this DFS search component by component. So component just means that if we have some, group of codes that sort of isolated with the other group, we definitely want to finish them all. So that given any particular course as an entry point to the graph, even if we explore every subsequent course, there can still potentially be some course we haven't looked at yet. So we have to try to go over all the course. And our ultimate goal is to take all the course. So this is going to be a loop. Can I change this? I'm just going to call this C. And for this two things, I'm actually going to use an array to indicate that. So instead of actually maintaining a stack, I'm going to use a recursive version of DFS. So the call stack, recursive call stack can be this physical stack Instead of coding a physical stack, I'm going to use the course stack. But for that reason, I have to use some indicating thing to tell me if a particular course is on the call stack. So I plan to use a Boolean array here. I'm just going to put it here. So it's taken, which is going to be size of how many? 10 to the 5th. So initially it's false. It's just Boolean flags. So if a particular course is taken, the ith location inside this array is going to be true. It's the same for the pass. Let's do the so just write a little bit more logic here. If this course has already been taken, then we continue to try to use other course as entry points to components there. Then we want to do the cycle detection. If the DFS function returns true, that means there is a cycle. That's indicative that there is no way that we can finish all those courses. Return false. Otherwise, we will, after the for loop, we just return true. So that's the main logics about applying DFS search here. Then let's do the graph processing. Just call this next courses. And yeah. For the pairs of prerequisite relationships, so the first item is the course that depends on the second item. So in our notation here, the prerequisites come before that. So it's a little bit natural to put the second one before as the key, as the access, as the index. So that's the graph processing. Then it's now time to define this Boolean function, which takes an integer. I'm just gonna call this DFS. We want to, I'm just lazy to grab everything here. Let's say that we are currently looking at the course. If this particular course, it's already marked as taken, as like the node 2 here. If we finish the first half first, then try this. We want to explore anything that's after 2. We first check if it's already taken. If it's already taken, we can. It means that from that point and on, there is no cycle. The way to detect the cycle is to see if this course is on our recursive call stack. So since that I cannot access the stuff on the core stack, I'm using this indicator kind of thing. After that, what we can do is to indeed put this onto the call stack. Mark this as true, and then do the DFS search on the subsequent branches. We're just gonna try to see if we can do, if we can find a cycle from that subsequent course and on. Sorry. So after this for loop, it's now our backtracking time. That's the time we can put the course onto taken, and we can also take the course out of mark this course as false to our pass, meaning that we have done with the pass from that course and on. We should go backtracking to the previous course on the pass and try to explore other branches over there. So just gonna change two things. Oh, sorry, true, and pass cost to false. Yeah, so this is the DFS function, and just put it on top there. Maybe. Yeah, so that's pretty much it. Let me quickly check. So we process the adjacency list to edge list to adjacency list, where the prerequisite course comes before the actual course, so that we can explore this way in a kind of a more human, natural kind of way. We take first calculus, then we take probability, then maybe statistics, something like that. So the DFS function, if it's already taken, that means we have explored the subsequent courses in some prior DFS tool search. There's no, so it's safe to return false. There's no cycle from that point at all. If this course is already on the current path, it means we indeed find a cycle. Then we're gonna actually put this course onto the path. After that, we will try to explore the subsequent courses from this particular course and all. If we find some subsequent course will lead to a cycle, that means, from my perspective, I need to tell whoever that asks me about this question, do we have a cycle? I need to tell him that there is a cycle, and relaying that message all the way back to the the entry point for this component, and from that point it's gonna be breaking. The cycle detection is gonna totally terminate, and early stopping the procedure, if you will. So that's this for loop. After that, it means either there's no course or a single course with no subsequent following up courses, or it's a whole branch of those courses have no cycle. Then we can just put that onto taken, and then it just means that we have already done with whatever course that's happening after that. We can mark this particular course as not on our path anymore, and go back to explore other branches. So that's this. Yeah. So yeah, let's see if it works. Arrow. Okay. Two. What's the problem? Do I have to do this? Oh, the size of this. Sorry. Let's try run example. This one works. Okay. All right. So that's the DFS solution to this graph cycle detection problem. In terms of time and space analysis, let me do a little bit time and space analysis. So this is upper bounded by the total number of nodes. If we use other kind of data structure, like we could definitely use an ordered map set for this taken, and for the path we can use a stack. So the maximum size is number of nodes. This processing here, the space is number of edges, edge, and the time is also the number of edges. So that's this for loop here. The DFS search, we're gonna explore all the nodes. So that's no escape. And doing the DFS search, we're gonna try to explore all the vertices. So this is guaranteed that we're gonna, in the worst case, we're gonna explore all the vertices, all the edges. And the reason that the importance of this, the taken C, to be checked, the first thing inside this DFS search is to avoid checking the subsequent graph multiple times. 1 leads to 2, 8 leads to 2. If we don't check that, then we're going to explore the subsequent graph multiple times. So that will lead us to number of edges squared times. So this check here will prevent that. Yeah, so if it's a naive backtracking, you probably just take this line off, and also maybe take this line off as well. So just get rid of the taken and get these two things out. Then it will be a naive backtracking. It will be much worse in terms of time. Just with this, memorizing which node from that node and on is totally okay. We can save a lot of time. Yeah, that backtracking is basically a DFS search. So in total, the time and space are both number of nodes plus number of edges, linear with respect to that summation. That's the worst case when we have to explore all the nodes and all the edges. The good thing is that if we do find a cycle early on, we can terminate it early. So compared to the topological sort, if it depends on the total ordering, to compare that with the length of the total ordering with the total number of courses, then you have to finish that. Maybe this is faster. Alright, so that's this question today.